AI research just crossed a strange threshold. Models are no longer only solving tasks, they're starting to run experiments, operate lab robots, and even bootstrap new training data from open research problems. That matters because the bottleneck is shifting from can the model answer to can the model keep making progress when the answer isn't known yet. Under the hood, the common pattern is agents getting more durable, more grounded, and much harder to fool. Here's what that looks like in science, in the lab, and in mathematics. Let's explore the first paper, Auto Scientists Self-Organizing Agent Teams for Long-Running Scientific Experimentation. Auto as Scientists, from Harvard University authors Shanghua Gao, Ada Fang, and Marinka Zitnik, introduces a decentralized, multi-agent framework for long-running scientific experimentation that replaces a fixed planner with self-organizing teams, shared experimental state, proposal critique, and dead-end tracking. Built on Anthropic's Claude Code with Claude Sonnet 4.6 and evaluated on H100 GPUs, the system improved over single trajectory auto research and other AI agents across BioML Bench, GPT, NanoChat optimization, and Protein Gym. On BioML Bench, it achieved a 74.4% mean leaderboard percentile across 24 tasks versus 66.07% for auto research, with especially strong gains in drug discovery at 64.52%. On GPT training optimization, it reached validation bits per byte 0.978 inches, 34 experiments versus 65 for auto research, and from a strong champion, it found 7 accepted improvements to reach 0.973, while auto research found none in 100 experiments. On Protein Gym, it extended Kermit into a 3GP ensemble that raised ACE2 spike Spearman correlation from 0.747 to 0.84, and when frozen across all 217 assays, it lifted average Spearman's row from 0.657 to 0.7. Ablations show that analyst roles, cross-agent feedback, and self-organization each matter, with the full system consistently outperforming reduced variance under matched compute. Let's explore the second paper, LabVLA Grounding Vision Language Action Models in Scientific Laboratories. LabVLA grounds vision language action learning in scientific laboratories by pairing a Qwen3 VL4B instruct backbone with a DIT action expert and a synthetic data engine called Robogenesis, developed by Zhejiang University and Shanghai AI Laboratory. Robogenesis generates 2,947 annotated assets, 1,000 plus textures, and 10,000 validated laboratory scenes, then composes long horizon workflows from atomic skills such as pick, pour, press, open, and stir across 16 robot platforms. The model is trained in 2 stages. Fast action token pre-training aligns the VLM with action semantics, and flow matching post-training with knowledge insulation decouples, language grounding from continuous control. Inference uses only 10 Euler steps. On Lab Utopia, LabVLA reaches 71.1% average success in distribution and 70% out of distribution, outperforming the next best policy, Pi 0, by 7.8 and 6.8 percentage points. The synthetic corpus is transferable. Fine-tuning XVLA on lab-embodied data lifts its 5-task average from 49.3% to 64.3% ID and from 43.7% to 63% OOD. A physical Franca study on 4 2-4-step laboratory tasks, each evaluated over 50 rollouts per condition, shows that the simulation-trained policy transfers to real benchtop manipulation, while pour liquid remains the hardest task across both simulation and hardware. Let's explore the third paper, Research Math 14K, Scaling Research-Level Mathematics via Agents. Research Math 14K scales research-level mathematics by converting open problems from the literature into agent-generated training data. The authors curate 1,233 academic sources from ArcSiv, ZB Math, workshops, and repositories, then use a 2-stage extractor-refiner pipeline to produce 14,056 self-contained problems, the largest public research-grade math corpus to date. They also release Research Math Reasoning, 220K teacher trajectories from GPTOS, S120B, and Qwen330B A3B, and show that trace quality is fragile. In 720 sample traces, 54% contain at least one fake reference, while newer model generations emit 5.6 times more reference-like mentions and 5 times more fabricated references per trace. A. GPT-5. D5 self-containment audit raises extracted questions from 67.2% to 94.2%, and duplicate filtering uses Qwen 3, embedding 8B with a 0.9 similarity threshold. Most importantly, LoRa fine-tuning Qwen 3, 4B, Qwen 3, 8B, and Qwen 330B, A3B on a 5,000 trace filtered subset improves downstream performance by 9.2 percentage points on average, outperforming a DASTI thinking control in 8 of 9 benchmark cells, and indicating that wrong but reasonable research attempts can still provide useful supervision after filtering hallucinated citations, non-attempts. That's a wrap on today's AI paper highlights. Thanks for watching.